Hey everyone, and welcome to This Explainer. Today, we're looking right under the hood to see how software actually translates our human intentions into machine actions. We're going to break down the language of code and explore exactly how text-based programming works today. Let's get right into it. To kick things off, I want you to think about a device you've probably used, well, thousands of times. Have you ever really stopped to consider how a calculator actually works? It's something we totally take for granted, right? But honestly, it is the perfect first introduction to programming. When you really look at a calculator, you realize it's basically a highly specific, pre-tested computer program. You, as the user, give it inputs. You enter numbers, you press certain buttons, and it automatically performs specific calculations. It takes those inputs, processes the underlying logic, and boom, displays the result. And it works perfectly because all of those rules were defined and tested long before you ever bought it. But what happens when we want to step beyond those pre-made buttons and define the rules ourselves? Well, that brings us to Section 1, From Blocks to Text. To build our own programs, we have to move past those pre-made buttons. For a lot of people, this journey starts with visual blocks. But to unlock the real power, we make the leap to text. Take a look at this comparison. On the left, we've got Scratch. It's a hugely popular block-based language where you use a graphical interface to just drag and drop these colorful blocks of code. It's safe, you know? You don't have to memorize specific commands, and the pieces just click together like building bricks. But now, look over at the right side. That is Python, a strictly text-based language. The crazy thing? The underlying logic is exactly the same. The program is still asking for two numbers, adding or subtracting them, and displaying a result. The key programming concepts haven't changed at all. It's literally just the way we input them that's different. And that brings us to a more formal definition. Text-based programming is, simply put, programming that requires the developer to physically type out the text to form instructions. It entirely removes that visual safety net of the drag-and-drop blocks. Oh, and by the way, a really fun fact from our sources, Python, which is one of the most popular text-based languages on the planet, wasn't actually named after the snake. Its creator, Guido van Rossum, named it after the comedy series Monty Python's Flying Circus. He just wanted a name that was short and unique. But, unique or not, to use it, you absolutely have to type specific commands. Moving right along, let's look at Section 2, Speaking the Python Syntax. So when you take away those visual blocks, you are relying entirely on the written word. And here's the thing about computers. They are incredibly literal listeners. They have absolutely zero understanding of context. In programming, this strict grammatical rule set is called syntax. Syntax refers to the precise structure of the code used in a programming language. Basically, if you don't use the correct structure, like say you forget a single quotation mark or slightly misspell a command, the machine simply won't understand you. Your program will flat out fail. Because of this, you really need a specialized tool to write and test this syntax. For Python, developers use an environment called IDL. That stands for Integrated Development and Learning Environment. When you type your text commands into IDL, it uses something called an interpreter. This interpreter acts like a real-time translator, turning your Python code into machine code. And machine code is the actual underlying language the computer's hardware understands to carry out your instructions. Okay, Section 3, 2 ways to code. When you launch IDLE to start working, there are two very distinct ways programmers write code today. The first is interactive mode. When you open up the Python shell, you'll see a prompt with 3 greater than arrows. Here, you type a single command, and it is carried out immediately. Bam! Right then and there. It's awesome for quick tests, but the big downside is that this code cannot be saved. Now, most of the time, developers want to write complex programs that they can actually keep. For that, they use script mode. In script mode, you open a text editor, write out multiple lines of code, save the whole thing together, and then execute it as one continuous program. And here is a massive pro tip for when you're writing in script mode. Use comments. By simply adding a hash symbol to your code, anything you type after it on that specific line is completely ignored by the Python interpreter. Programmers use this all the time to leave human-readable notes for themselves or for their teammates. Like you might write, hashtag, the next few lines give the introduction, if you are building a digital sweet shop game. It vastly improves the readability of the code for humans without breaking the machine's rigid syntax. It's a total game changer. So let's actually walk through the exact real-world steps a developer takes to build a finished Python script. First, from the Python shell, you select New File.
Easy enough. Second, you type your beautifully structured, syntactically correct code, along with your helpful comments, of course, right into the text editor. Third, you save it. You'll notice it ends with a .py extension showing it's an official Python file. Finally, you go up to the menu and click Run Module, or honestly just hit F5 to execute the program and see your outputs. Now for Section 4, Storing Data with Variables.
A program isn't very useful if it just does the exact same thing every single time, right? We need it to be dynamic. We need a way to store data on the fly, like capturing a user's answers when they play a game or finish a math problem. And this introduces the concept of a variable. A variable is essentially a named memory location used to store data while your program is running. Think of it like a designated storage box that maps directly to the system's memory. You give the box a name, you put a piece of data inside it, and, crucially, the value inside that box can change or vary as the program executes. Take a look at how we actually write this out in Python. In the code right here where it says name equals Ardeel, the variable label itself, the actual word name, is not inside quotation marks. We are simply telling the computer, hey, create a box called name and store the text Ardeel inside of it. And we do the exact same thing for age, address, and favorite color. But how do we get that stored data back out to the user? We use the print statement, combined with a very specific piece of syntax, a comma. By writing print, opening your parentheses, putting quotation marks around the text, your name is, closing the quotation marks, adding a comma, and then typing our variable name without quotes, well, the computer seamlessly joins our static text with the dynamic data stored in the variable. It's kind of like magic, but it's really just pure logic.
All right, Section 5, Squashing Coding Bugs.
Of course, as you write more and more lines of code, you are eventually going to make a mistake. It happens to literally everyone. Remember, Python is strictly case-sensitive. Notice the glaring red name error here. A developer tried to print Hello World, but they capitalized the P in print. That single tiny capital letter completely breaks the entire program. To fix it in script mode, you have to physically go back to the text editor, change that capital P to a lowercase p, save it, and run it all over again. Because these errors are so common, professional programmers don't just guess if their code works. They systematically hunt for bugs using what's called a test plan. Before they even run the program, they map out the tests. They write down exactly what data they're going to enter, say 5 and 6, and explicitly state the expected outcome, which should be 11. Then they run the code and record the actual outcome. If the actual outcome matches the expected outcome, it's a pass. If not, it's a fail and it's time to debug. It is a highly meticulous, structured way to make sure the logic perfectly matches reality. And that structured logic brings us completely full circle. We've transitioned from the predefined buttons of a calculator to the drag-and-drop safety of Scratch, all the way to commanding the computer directly using text in Python. You now understand the absolute importance of strict syntax, how to navigate idle script mode, how variables act as storage boxes for the world's data, and how test plans squash those inevitable bugs. The machine is waiting, ready to literally execute whatever you tell it. So my provocative question to leave you with today is this. Now that you know the grammar, what will you build when you speak directly to the machine? Thanks so much for joining me on this explainer, and hey, happy coding.